Hi guys, welcome back to Hop into Precalculus. In this video, we're diving into 1.4 and 1.5, where we will learn about polynomials and how to find their roots, even imaginary ones. Whether you're starting AP Precalculus or need a quick refresh, I've got you covered. The topics I will be talking about in this video are 1.4, polynomial functions and rates of change, and 1.5, polynomial functions and complex zeros. So what even is a polynomial? It's a mathematical expression that uses variables and coefficients, and we have one right on the screen. So this is the leading coefficient, which affects if the polynomial points up or down, and its end behavior. Second, this is the degree, which is the highest exponent that one of the variables has. Lastly, this is the constant, which has no x. Some polynomials have specific names depending on their degree. For the first one, linear, it has a degree of 1, and the parent function looks something like this. Next is the quadratic, which has a degree of 2, and the quadratic looks something like this. Lastly is the cubic, which has a degree of 3, and that one might be new, and it looks something like this. Local and global extrema are new vocabulary, so I'll explain them. Local extrema is a point or a value that is higher than things that are close to it. For example, here, it's a greater number than where it's close to here. And then here is the local minima because it's less than its surroundings. This is a cubic function. And that means since it's odd, it can't have a global extrema because it will extend infinitely up and down and there will be no maximum or minimum value. Even degree polynomials do have global extrema because of the way their shape is. You can see this one, the end behavior extends towards infinity. So that means this is a global minimum. And then this one extends downward. That means it must have a global maximum. Now on to solving polynomials. So here we're given a quadratic, and if you remember anything from previous math classes, you can factor this into this. And then you get and those are your roots. And then because they show up only once, then we say their multiplicity is 1. And for this one also. And then this is a quadratic. So we can graph it by graphing the roots, -1 and -3. And then since it's an even one, then the end behavior will be the same for both sides. And it will look something like this. This is something that probably will be new to you, and it's imaginary roots. So back then, when people had the equation x squared equals -1, they didn't know if there was an answer or not, so then they just came up with a imaginary unit called I. So I is defined as the square root of -1. And then in a polynomial, whenever you have one imaginary root, you have to have the conjugate. So for example, you solve and then you see you have 3 plus 4i, and that's one of your roots. So that means 3 minus 4i must also be one of the roots since they always come in pairs. Lastly, we will talk about odd versus even functions. So on the left side here, we have odd functions. They have an odd degree, obviously because they're called odd functions, and they're rotational symmetry. That means you can rotate them and then it will end up looking the same. Also, f of negative x equals negative f of x. So let's say x is 1 in this case, so f of negative 1 is negative 1, and negative f of 1 is 1. On the right side here, we have even functions, which have an even degree. And they are reflectional because you can reflect them across the y-axis. Here, f of negative x equals f of x. So we can say, again, x is 1, and the f of negative 1 is 1 right here, and normal f of 1 is also 1 right here. It's time for a practice problem. So it tells us that we are given the expanded form of a polynomial function. And then we had to answer the questions what the degree is and what type of function it is. So first we can see the degree is 3. So that means this function is a cubic. Okay, next we need to factor the polynomial and identify all roots, including complex ones. We also need to state the multiplicity of each root. Okay, so we can rewrite it here. And then we can factor this by grouping it. We can group these two and these two. So when you look at these for the first group, you can factor out an x squared, and you're left with an x minus 2. And then for the next one, you can factor 1 out of them, and you're left with an x minus 2. And that means you can combine these into x squared plus 1 times x minus 2. And now we can separate these and solve for them separately. So x squared equals negative 1. This is something we saw earlier. You just take the square root of both sides and you get plus or minus I since it's x squared. And then we can solve for x minus 2 equals 0. So that means x equals 2. So we have our roots. And then it tells us to state the multiplicity of each root. So the multiplicity of negative I is 1. The multiplicity of normal I is also 1. And the multiplicity of 2. This is kind of a review of something in the previous video, and it also includes rates of change in polynomials. So this is the graph of x cubed, and we need to find on what intervals is the function increasing, if it even exists. And then here we can see that if you trace it from left to right, it's always going up. So that means it's always increasing. And the interval is negative infinity to infinity. So because it's always increasing, that means it will not be decreasing. So it has no intervals that it's decreasing in. And lastly, what intervals is the graph concave up, and where is it concave down? So here we can see the rate of change is decreasing and is becoming less steep. So that means it's concave down from negative infinity to 0. And then when it's from here all the way to here, you can see the slope is increasing. So that means it's concave up. Thanks for hopping by. If this helped you, make sure to leave a like and subscribe to help other people see this video. If you have any questions or any topics you want me to cover next, you can leave them in the comments. Here's your bunny reward.